Hi folks. Today we're looking at limits involving infinity. And to do that, I think the most important graph to imagine is this one here, our basic 1 over x. Our most basic hyperbola, or I like to call it just a butterfly looking graph. This is a great graph. I mean, it explains why division by 0 is so contentious, that it's different from the left and from the right. And it also shows us a bunch of really important limits. So if I were thinking about the limit as x goes to 0 from the left on this, let's check that out. X goes to 0 from the left. Oh, that goes down to negative infinity. The limit as x goes to 0 from the right, well, that goes up to positive infinity. If I thought about the limit as x goes out to infinity, what does that mean? Going out towards positive infinity means going to the far right. So maybe I'll pick a different color here. Do this in pink. Okay, head out all the way here. Well, that's going to go towards 0. Now, when you head out towards infinity, it's implied that you approach it from the left. You can't come at positive infinity from the right. And then similarly, if we went out towards negative infinity, okay, so these are x values, we'd be talking about going to the far left. So let's pick out another nifty color here. This peach. There we go. That's also going to go towards 0. Now, just imagining that, what if you put in negative big number here, like a negative a bajillion? 1 divided by negative a bajillion is really close to 0. Same thing if you put in 1 over positive a bajillion. It's closer and closer to 0. Okay. So these ones here, this means far right, and this one here means far left. We're going to deal with the first two kinds first, though. And it's going to give us a calculus definition of a vertical asymptote. Okay? The line x equals a is a vertical asymptote if, that if with two f's means if and only if, the limit from the left is positive or negative infinity, or the limit from the right is positive or negative infinity. So if a limit is infinity or negative infinity, we have a vertical asymptote. Now this seems kind of backwards because usually you'll recognize that the limit's positive or negative infinity because you know about the asymptote. Let's try a couple out. So let g of x equal ln of x minus 4. All right, let's think about that graph. That would be a basic logarithmic graph, but it would be shifted 4 to the right. So 1, 2, 3, 4. And a logarithmic graph has a vertical asymptote. Okay, and so g of x, I'm going to do in blue here, is some just quick and dirty sketch, something like this. So as we approach 4 from the right, we're going down towards negative infinity. The other ones have to do with h of x, which is tan x. So let's graph tan x. Maybe it's been a little while, but it's got asymptotes. We know it, pi over 2 and negative pi over 2. Okay. And it does its thing, which looks kind of like this. And then it does its thing again, over and over. So as we approach pi over 2 from the left, we're going up towards positive infinity. As we approach it from the right, that's what this x pi over 2 with the plus on it means. Yeah, it goes down to negative infinity. Remember, infinity is not a number, though. It's an idea. And the overall limit is different from each side, so we would say that it does not exist. TNE for the overall limit. So here's a little graph for you to think about. Maybe pause and think about each of these 4 limits. And we'll unpause. Let's see if you ended up with the same answers I did. I got these, so I'll just go through them one at a time, starting with the first one. 1 from the left. It's going down like this. That's negative infinity. 1 from the right. It's going up like this. That's positive infinity. As x goes to infinity, that is to the far right, we appear to be closing in on a value of 2, okay, because that's a horizontal asymptote. And as x goes to negative infinity, that's the far left, it's snaking around the number 3, but it is closing in on it. It's converging in on it. So we'd say that the limit is negative 3. So that's how we can do it from a graph. The next question we likely have is, okay, well, how do we do it analytically? And I've got a limit here involving infinity that we could approach 4 ways we'll take a look at. If I just sub in, though, let's think about that. First of all, you can't really sub in infinity. You get 5 times infinity cubed minus 3 infinities plus 2 all over 2 infinity cubes plus infinity squared minus 1. What is that? Well, that's essentially infinity over infinity. Okay, but there might be a ratio between those that is important. This is one of those other indeterminate forms. So there might be something that it's zeroing in on. And I'm going to show you, first of all, we'll do the analytic way, because there's a really beautiful idea that somebody came up with here. They said, all right, that doesn't help, but what if we rearranged them so that we had terms that were kind of like this, that it were like had 1 over x squareds or something. And as x goes to infinity on a 1 over x squared, well, you could think of that as 1 over infinity squared. But just thinking about it, 1 over infinity squared, 1 over really big squared. If you have one chocolate cake and you have to split it between infinity people, everybody gets next to nothing, right? The limit here is going to be 0. So when we have them written this way, as fractions with the x on the bottom, things are easier to deal with in infinity land. And that gives us sort of a full-service analytic way that we can take a look at this. What I'm going to do in this fraction is I'm going to look at the highest power that's on the bottom, which is an x cubed, and I'm going to times both the top and bottom of this big old fraction by 1 over x cubed. Now let's see what that gives me. Well, 5x cubed by 1 over x cubed will just give me 5, which is pretty straightforward. So x goes to infinity. The next one is going to be 3x over x cubed, so that's minus 3 over x squared. And the last one would be 2 over x cubed. So I'm building nested fractions, which is kind of a weird thing to do. 2 over x cubed. What's going to happen on the bottom? Well, I'll have 2x cubed times 1 over x cubed. Oh, that'll be nice. That'll just be 2. And then I'll have x squared times 1 over x cubed. Oh, geez, that'll just be 1 over x. And lastly, I'll have negative 1 by 1 over x cubed. So that's not positive, but negative 1 over x cubed. And as x goes to infinity, let's think about each of those. I mean, I don't want to write subbing in infinity because we've said before, it's not a number, but I'm going to put it in a thought bubble to get away with it. Plus 2 over infinity cubed. 2 plus 1 over infinity minus 1 over infinity cubed. Well, 5 is always just 5. This guy right here, 3 over infinity squared, that is basically 0. Okay. This one right here, 2 over infinity cubed, that's also 0. 2 on the bottom. This one right here, 1 over infinity, that is 0. 1 over really big is 0, or its limit is 0. And lastly, this one, 1 over infinity cubed, that's also going to be 0. So allegedly, what's going to happen here is we're going to end up with 5 minus 0 plus 0 all over 2 plus 0 minus 0, or 5 over 2, or 2.5. which seems really weird because you can't sub in infinity. But as we go out to the far right, this function should be getting closer and closer to the x value of 2.5. That's a nice full-service analytical way to do it, but it's a lot of work. Another way that you can do this is just numerically. And the name of your textbook is Calculus, Graphical, Analytic, and Numerical in some order. So if you want to find an approximation of what happens at infinity, just sub a big x value in. And you might think, well, infinity, I need to use, 100 bajillion. I'm just going to put in 100 to start with and see what happens. And I'm just going to use a calculator. So the function was 5x cubed, so I'll put in 5 times 100 cubed minus 3 times 100. So 100 is just my estimate of infinity here. I could use a bigger number if I wanted to. This is all over 2, 100 cubed, plus 100 squared, and then minus 1. And I'll just hit equals. And you can see it's 2.48. It's really fishy. If I used a number that was closer to infinity, whatever that means. So if I used 1,000. All I've done is used a bigger value. You can see it's getting closer to 2.5. And doing two of them really confirms to me that it's converging or getting closer and closer to that value of 5 over 2 or 2.5. That idea of numerically hacking a limit is really, really important. If for any limit you're ever not sure what it is, just choose an x value that's really close to the one that's in question. So for infinity, I used 1,000, just a big x value. All right, better yet, let's look at the graph. Here's the graph. It's super weird. But if we're looking for the limit as x goes to infinity, that means tracing it out far to the right. And I can see as I go far to the right, the y value, it's getting closer and closer to, it looked like a 2.4-ish. And I can keep going out. Maybe what I want to do here really is just zoom it so I can see, oh yeah, out around 200, we're getting closer and closer to 2.5. And I can zoom it even more. You can see it's going to lie to us eventually. It's not actually at 2.5, okay, but it's going to whatever, 4 sig figs and doing its best. We're getting closer and closer to 2.5 or 5 over 2. So if you have a graph, graphical method's great. What I think the best method is, though, is this one, lazy analytical. So when I look at this function over here, or this limit expression, as we go out towards infinity, not all the terms mean as much as each other. So 5x cubed, 5 times a bajillion cubed, compared to this 2 right here. Nobody cares about 2 out around infinity. Imagine if you had $1 trillion. Would you care that much about every toonie? Probably not. Right? There's orders of magnitude involved. So the highest power on top and bottom is really what's in charge. Even the minus 3x compared to the x cubed is nothing. Okay? $1 million is nothing compared to $1 million cubed. And we're heading out towards infinity, so these disparities make even more of a difference. Here's how I think of it. I think this term is in charge on top, and this term is in charge on bottom. I call these terms drivers. And if I want to find this limit, and this is only true as we go to infinity or negative infinity, for a basic rational, you can just think about what's going on with the drivers. Out around infinity, none of the other terms matter. And that's an easy limit to work out. Okay, x cubes divide out, bam, 5 over 2. So we've looked at formal, numerical hacks, graphical interpretations, and finally this lazy analytical approach, which I think is real good. So to recap, if you want to find the limit as x goes to positive or negative infinity in a rational function, that means a fractional function, the formal way is set up the limit and divide every term by the highest degree on bottom and then evaluate, or use the shortcut. Limit of highest power on top divided by highest power on bottom, or use the drivers. When the limit as x tends to infinity or negative infinity turns out to be a constant, that means we found a horizontal asymptote. Okay, so in that other one that we just looked at, there was a horizontal asymptote at 2.5. That's because of the limit. And up to this point, horizontal asymptotes have been tricky to find, but now we've got this calculus definition. Just look at the limit as you go to the far right. So over here, we could do this. I'll do it just real quick the formal way. We would times it by 1 over x squared on top and bottom. And that would give us on top 3 minus 2 over x. And on bottom 2 plus 1 over x squared. And as we went to infinity, that would be 3 minus 0 over 2 plus 0, or 3 over 2. Bam, we're done. Okay, that's full service analytic. Here's lazy analytic. Lim as x goes to 0, 0 over 2 plus 0, or 3 over 2. Bam, we're done. Okay, that's full service analytic. Here's lazy analytic. Lim as x goes to 0 of 3x squared minus 2x all over 2x squared plus 1. Here's the driver on top. Here's the driver on bottom. And this is a trick we can only use as we head out to infinity or negative infinity. Just consider the drivers. Everything else is fluff. Okay, around positive or negative infinity. And that gives us 3 over 2. Pretty slick. Let's try another. On the top in this one, we've got this as the driver. On the bottom, we've got this as the driver. So let's evaluate this limit. That would give us negative 5 x4 all over 2 x5. And this reduces, but not completely. There's still an x involved. So that'll give us lim as x goes to infinity of negative 5 over 2x. That is something that you can evaluate. I mean, imagine putting infinity into that. I'm putting it in a thought bubble because you can't really sub in infinity. Negative 5 over 2 times infinity, that's going to be 0. Or if you're having a hard time thinking about that, think of it as putting in a big number. 2 times a bajillion. That's going to be something very, very small, okay, because you've got a big denominator. So this is heading towards 0. So this means negative 5 over 2 times infinity. If the highest power is in the bottom, you're heading towards 0. Okay. That means this function has a horizontal asymptote of y equals 0. And this function back here has a horizontal asymptote of y equals 3 over 2. Okay, whenever the limit turns out to be a number. Lastly, it can get kind of complicated when we have radicals as well. So radicals are less full service than exponential notation. A square root is x to the power of a half. So x to the 3 over 2 plus 1. And I'm going to put it in this exponential terms before I start dealing with this. So that's 3x to the 1 times x to the half. When you multiply with the same base, you add the exponents. So you might say, oh, that's 3x to the 1.5. But our days with mixed numbers are probably done. 1.5 is 3 over 2. And this is not the only way you could do this question, but it may end up being the slickest way. Once we see that, the highest power on the top is x to the 3 over 2, because this would be an x to the 1. So there's our driver on top. Here's our driver on bottom. And because it's a lim involving infinity, we can just look at those drivers. And divide out. What are we going to get? We're going to get 3. I guarantee you that this function has a horizontal asymptote. Not that that's what the question asked to begin with, but it does have a horizontal asymptote of y equals 3, at least on the right-hand side. This function doesn't exist for negative numbers, though. All right, that brings us back to the squeeze theorem. So we're asked here to find this, use the squeeze theorem or sandwich theorem to find this limit. So what we do is we take sine of whatever we've got, and we know that that is sandwiched between 1 and negative 1. Okay, and now build sine x over x, which is what we've got, okay, by dividing all pieces by x. Now someone at this point is going to say, oh, that's just supposed to be 1. No, 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 no. The lim as x goes to 0 of sine x over x is 1. But this we don't really know yet. So using the squeeze theorem, we would divide each piece of this by x. And hopefully we would get stuff that is easy to evaluate. I'm going to find the lim as x goes to infinity of this. Well, that would be negative 1 divided by incredibly big, so that would be 0. I can find the lim as x goes to infinity on this, which would be 1 over incredibly big, which is 0. And from that, I can also determine that this limit, since it's sandwiched between 0 and 0, must be 0. Now, squeeze theorem isn't the only way to do this. I think it makes a lot of sense just to go, well, sine x is something between negative 1, that's a smiley face, and 1 over infinity. I mean, that's going to go towards 0. That's what I'm thinking as I look at this. The other thing I can do is look at the graph. Right on the graph, I can see that it's getting closer and closer to 0. I could move over. And I could also see the sandwich theorem or the squeeze theorem at play here. That graph is squeezed between 1 over x and negative 1 over x. Okay? And even without the sign graph showing, you can see that that graph, as we head, those two graphs, as we head out to the far right, they're going towards 0. And since sine x over x is sandwiched in between them, it's also heading towards 0. And we get these lovely graphical interpretations. So once we know this fact, that the lim as x goes to infinity of sine x over x is 0, we can use it in some other limit. So if we wanted to find the lim as x goes to infinity of 10x plus sine x over x, I mean, I can split those into little bits. Okay. And the x's here could divide out. You can do all sorts of wild stuff before subbing in limit land. And so what will we get? As x goes to infinity, 10 is just 10. And sine x over x as x goes to infinity, we just showed right here, is 0. So this one should be 10. And you can take a look at the graph and verify that. Once we have this idea that we can look at the drivers and just imagine big numbers, some of these questions get a little bit easier. So if we want the limit as x goes to infinity on this one, so as x goes to infinity, well, what's going to happen? I can do this all in pieces. The 2 is going to stay at 2. This will be x squared over x squared, so those will just divide out and give us 1. In this one, it'll be driver over driver. The x cubes will divide out, and we get 3 over 2. We do not care about this 2 or this x. They are inconsequential around infinity compared to an x cubed. So in other words, we get 1 times 3 over 2, or just 3 over 2. I guarantee you that that really complicated looking function just converges around 3 over 2 as we go to the far right. In the other one, as x goes to infinity, sine 1 over x. I mean, let's think about that. That would be sine of 1 over infinity. So that 1 over x limit can be an interior part. As x goes to infinity, 1 over x becomes 0. So we get sine of 0. And sine of 0 happens to be 0. Okay. So this one's going to converge on 0 as we go to infinity. So thinking informally or thinking about those drivers, things can go fairly quickly. That gives us some stuff to do on page 76 of Finney. A couple of spots there. And there are some questions from a worksheet from Stewart. There's a second part to this lesson that will deal with end behavior models. But for now, that's as far as we'll go. There are some for fun questions, quote, on the Stewart page, some challenging limits there in some places. I hope that you found this helpful. Good luck with the material, and take care, folks.